In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwini, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast. So I'd like to ask you first, how you'd like to define who you are for the audience, maybe first time listening to you.
Yeah, so my name's David Howard, and I'm a senior research scientist at CSIRO, which is, so I'm based in Brisbane in Australia, and I'm part of the Robotics and Autonomous Systems group there. So we focus on field robots, so robots that need to go out into the real world, do real things. So, I think the most famous example recently has been the DARPA Subterranean Challenge, where we finished second, joint first on points, with the eventual winners. And that's the type of thing that we do. We take robots, we make them go out and work, and work in sort of nasty environments as well. So that's kind of where I come in. I mean, my background's, my PhD is in genetic algorithms and neuroevolution and things like that, which I did in England. And then I came over here, and then I got into soft robots. And I just think the kind of marriage of evolution in soft robots in the domain of field robots, kind of in particular, is really, really an exciting one.
So thanks so much, and also congratulations for that recent publication. I think it's very interesting and touching, really challenges in soft robotics. Maybe I'm curious to ask you in the beginning, from your experience, maybe what are the grounded challenges you think in robotics that still need more pushing to forward? What kind of the problem do you think still not touch it in depth in robotics yet?
Yeah, well, man, it's a good question. Like, so as someone who kind of hopped into soft robotics not quite at the start, I think there's a couple of things. Soft robotics as a whole is this kind of nascent field, right? And it can be in some ways construed as more of an art than a science, specifically around the design. There has been a lot of really interesting work recently, and I don't want to short sell any of that, but I think compared to designing a rigid robot, for example, the challenges are just so much more difficult, but they're also far more interesting. And I think specifically one of the things that we're looking at right now is how, if you're training a machine learning model to represent a design space for you, how do you do that? Because, if you're using a model of a soft robot, you're using, I don't know, VoxCAD, or you're using FEA or something like that. They've all got certain limitations to them. They're all great pieces of software. They've all got certain limitations, specifically around the reality gap. So how do you sample reality properly? Especially with these, infinite degree of freedom soft robots. It's a very, very difficult problem. And then coupling that with control as well, things get a little spicy, and you have to really, really think about, what is the key problem that you want to be tackling, and is there a way that you can frame it in such a way that you can solve it? Because it's very difficult to do everything all at once.
That's an excellent point. So maybe the first thing, how do you think, you mentioned one of the paper that if you really represent more dynamics of the problem, it could maybe reduce the reality gap. And also we speak with Res Tedrick about, he also was TRI developing Drake. I don't know if you heard about Stool,
Yeah.
but yeah, he said that much simpler mathematics may be the solution. I don't know, from your research, you mentioned if we have more representation of dynamic system, and that lead me to the question about the design. You mentioned it's more about art. Do you think in soft robotics we don't have, I don't know, we have, do you think, rigorous design methodology for designing soft robots so far?
I think we do in certain spaces. So, soft robots is this whole massive, varied, diverse field full of all kinds of, strange articulated or continuum devices. Some of them can be modeled quite nicely. And, kind of, I'm thinking kind of continuum pneumatic actuators, for example. They're relatively easy in a way to model. A lot of the work that we do in my team, the material robotics team, is around granular jamming. And that's one of those sort of soft robotic subfields where it's very difficult to get that modeling right. You can, so to kind of frame the issue, this is kind of the famous sort of universal jamming gripper, right, where we have essentially like a latex balloon, fill it with coffee grounds, and you attach it via a filter to a vacuum pump, and you can pick up loads of different objects with it. And it's really interesting, simple sort of innovation back in 2010, when that sort of first paper came out. And there has been some effort on the modeling of these devices, but the problem is, like, you've got all of these individual grains, and do you model them as individual grains, like in discrete element method? Can you have like a compressible fluid model instead, and then you lose some of the reality from that? And the types of models that we're looking at now are kind of DEM, and you've got all of these different particles and you're solving each individual contact between the particles, and it becomes intractable past a certain point, right? And those systems are difficult because you've got the effects of the shape, the morphology, the material properties of the membrane, and then if you do what we do, which is 3D print the grains that go inside, you've got the material properties, the surface finish, the softness or rigidity, the shape, combinations of different shapes within that membrane, and then they're all interacting potentially in a very complex environment. So that, again, that's why I like soft robotics. It's difficult, but it's also one of these really sort of challenging, rewarding things where you kind of feel like you can make a difference. So yeah, I think that the field really has come a long way in a very short amount of time, and it makes me really optimistic for the future, and specifically, what we can do in the next sort of 5-10 years or so, in terms of having some of this kind of foundational stuff, but also really seeing useful outputs delivered into industry, which is what CSIRO kind of focuses on. We're kind of the national science body for Australia. And that's one of the main challenges that we have, right, is we are seeing lots of issues around agriculture and labour shortages and stuff, and, reimagining, for example, what farming might look like in 10 years' time, and the role that soft robotics has to play in that. And I think that's a rather large, significant role if we do it properly.
That's a good point. I think we will go for that later about maybe the potential behind soft robotics for real world application. But I'm curious to ask you, I think, touching again on the morphology side, because I think also in soft robotics we speak about co-design, and still is not really well established in the field, and how we can bring this to paradigm, the digital computation with morphological computation. And I really like your research about how the morphology can adapt to uncertain environment and how controlling morphology in real world scenario. Can you tell more about the challenges of morphology, and what do you think maybe
not touch it in depth about the morphology consideration to be changing and adapting to different environments.
Sure. Well, I think, specifically with soft robotics, the issue is that you could give the same control commands 100 times in a given environment, and depending on, the specifics of the bit of the environment that you end up interacting with, you'll get some completely different results. And, things like state estimation, for example, very difficult to do in some cases. I think the co-design problem is really interesting because you immediately start hitting this kind of curse of dimensionality thing, right? Where you're designing you're sort of following the principles of embodied cognition, which I think is a really good lens to view soft robotics. We've got this issue of, we've got a body, we've got a controller, but then if we change the body a little bit, your controller could break. If you change the controller a little bit, your body could be less used, for example. And then you're doing all of this in the context of a kind of unpredictable, unknown, dynamic environment. So there's also issues around, like, how do you sample the environment, and going back to the modeling, like how do you represent different environments, specifically in the context of FEA? Like you're playing with constraints and forces, and it's very hard to capture the effects of an environment in that case. You're not really, FEA isn't really set up to do that. But if you go into like a physics simulation, then in a lot of ways your models become less accurate, and then the results aren't quite as good. So I think there's a lot of work to be done in kind of maybe marrying those two together somewhat. That would be pretty cool, pretty interesting. The naive way of doing the co-design is like I'll change my body. So like in the genetic algorithm case, for example, let's say we've got a population. So we're doing population-based optimization. We've got this population of 20 different morphological combinations, so different bodies, shapes and sizes and whatever. And depending on what representation you use, like if you use an indirect representation, which is attractive, for a number of reasons, then you've got some issues just with the morphology without the control, because the indirect representation, again, you make these very small changes, you break things quite easily. And then you add the controller over the top, and all of a sudden you're optimizing hundreds of iterations of control onto a single iteration of a body, and you get this sort of computational overhead, which is, if you're not smart about how you do it, it's basically impossible to surmount even through simulation. So when you talk about doing that in reality and having it work in reality, it's an entire other problem as well. And, we've been doing a bit of work recently around co-design entirely in reality. We're basically, there's this concept from materials science of the high throughput highway. And it's basically, they have these kind of just very simple XY gantry robots with little sensor heads on them. And they can go up and down these little vats of chemical. And I hope I'm not butchering this for the material scientists, someone is. And they can sort of infer properties of different chemicals, and then they can optimize those chemicals, but they're doing like thousands and thousands of times faster than a human can. So that's for materials. You could, theoretically do the same for soft robots if you had the facilities, the infrastructure to do that. Mm-hmm. That's one of the things that we're having a look at right now, which is like, if we had a reprogrammable controller, which most are, then we can actually just do pure hardware evolution of a soft robot. And what we're looking at, we don't think this is the final answer. We think the final answer is a combination of this plus modeling. And there's Yeah, there's a recent paper from Fumiya Iida's group which says basically the same thing, and is the same as kind of conceptually similar to what myself and a few others were saying in our nature machine intelligence paper on multi-level evolution, which is like, yeah, you need some hybridization. You know, you need the models to be fast and cheap and parallel, but you also need them to capture enough of reality and be fed enough real information, so that you can optimize in that space, and that space has a meaning when you then instantiate it in the real world.
Mm-hmm. That's great, but I'm just asking you, do you think there may be very complex problems, do you think, can be handled by the recent methods we have? Do you think maybe the design, should we rely more into intuitive design if we want to achieve complex problem, like using different materials to achieve certain functionality? Do you think there's still sort of problems you think still hard to be handled by, for example, optimization only, and maybe intuitive design could be a first approach? Or how do you see this philosophy of the design? Do you think we have to go for intuition and then maybe leading and figure out how could design can handle such complex problem to achieve, for example, certain functionality, whatever you're looking for?
Yeah, and so when I said at the start that software robotics is more of an art than a science at the moment, that's not necessarily a bad thing. I think it's a field that really rewards creativity. And a lot of the work that we've done so far has been, our engineers, which I've introduced into the world of software robotics, coming up with really amazing ideas, just from being exposed to this kind of new and interesting, and it's a field that's a little bit different compared to the standard kind of mechatronics work that they do. And I think there's a bit, again, like the simulation in real, the answer for me is a little in the middle. As humans, we're not dumb, and we do have good intuitions about designs, but we just lack the ability to parallelize 10, 20, 30 designs at once, so if I ask you to make me a software robot that swims, you're probably thinking of a fish. Or, in software robotics, you're probably thinking of an octopus, actually. But you have this sort of preconceived notion, right, of something from nature, so bio-inspired, great, that swims really well. And then it's like, oh, well, let's try and make that with soft materials. And that's a completely valid approach. The way we do it is we consider one of our goals to access as much of that design space as possible, and then rely on the bias-free evolutionary algorithms that we use to give us a principled look into that design space. So, there are lots and lots of weird and wonderful animals in nature. And, if we want something fast, we're going to think of one of the big cats, maybe, or a zebra. But there are other animals that do fast in different ways. And maybe some of those are more suited to be recreated as soft robots, or maybe we can even think of the mechanisms that they use rather than the animals themselves. Steal bits of mechanisms from different animals and have a bio-inspired kind of toolkit of different actuators and different sensors with different kind of performance ranges. So that would be interesting. But I think for me the answer is we want our engineers to be using their engineering knowledge because they're good engineers. And we want to be leaning on these algorithms as kind of, we had a paper where we called it design assist. And I don't think we were the first people that came up with that. I think I read it somewhere, so I need to be careful with that. But it's basically the notion that, these fast parallelizable models can aid human designers in exploring these spaces that their brains aren't equipped to fully visualize. And then, you could think about evolution being a coarse-grained search over that landscape, and then the engineers can come in and use some intuition and kind of do a local search around that. So that's kind of the philosophy that we're going for at the moment. So what we're trying to implement. And it's been promising so far, but no no results to talk of yet.
Great. Okay. So I guess it's key about the relation specifically between the morphology and control. And I don't know, how do you see we can leverage the richness of the body, for example, versus the control? Do you think, should we minimize the control? Example, you mentioned that we have a legged robot, but if we speak about like fully soft robots, do you think how the scenario looks like, this combination morphology and control and this environment changing, which one, do you think that you can leverage the richness of the soft bodies and use minimal control? How do you see the equation here between control and morphology towards in changing environment?
I see. So, my personal thoughts on this is that we need to get some reactive kind of sensing actuation mechanisms into the body material. Much like, I mentioned octopuses before. They have arms that can basically control themselves, and it's coordinated through the brain. And that's, an octopus, being an octopus, I imagine, is a wonderfully difficult control problem to have. So I think, our preference is 3D printing, so we do a lot of stuff, trying to embed sensors and actuators into body materials to really leverage the body. And the problem, again, there is, if you were going to take your standard engineering approach, you would go and try and reduce that into component units and then solve all the component units and then bolt them back together. And that's great for a rigid robot, but you can't really do it with a soft robot because you're looking at the whole body interaction. And again, like, if you take that octopus, which displays these wonderfully clever behaviors in its environment, and you go and stick it somewhere else, it's not going to behave very well. So it's really having that coupling with the environment as well. And, so there's the notion would be you would have body material which you can create in free-form fabrication, whatever shape you want, ideally, and then inside this material you have the equivalent of a nervous system which is locally connected, which can react instantly to environment that it senses, but those signals are also passed through to a central unit, the brain, which coordinates all of that. So having the intelligence literally distributed through the body, again, it's not an original thought in terms of we see it in nature, but I think to answer the question, we need to look for natural creatures which we would struggle to generate control software for. And those are, the continuum devices, fully soft. And we look for how those solve the problem. And they solve the problem in the way I described. They have the knowledge, the intelligence is literally in the body.
Mm-hmm. Excellent. So I guess this could also gain about uncertainties like damage, how this soft bodies can adapt to do damage. And what are you doing? This combination, morphology, control, environment, damage here, the equations damage, how they can adapt to the damage. And do you think there's limitation depending on the morphology? I'm curious about the scenario like that, the failure of damage here. How they can adapt.
Maybe Josh Bongard's pretty recent work where he actually evolves soft cellular animals that are made of living cells. That would be a route towards it, although it's very sort of nascent. But the proof of concept is there at least. I think another way that you can do is kind of, maybe a more near-term way of doing it is just to make do. If I twist my ankle, I'm hopefully not going to die, right? But it's going to be more difficult for me to adapt. And there's been some good work around, let's say I have a model of myself, or a soft robot in this case has a model of itself. You can damage that robot, and the model will be able to instantiate damage recovery in some way. It will find a locomotion strategy, a behavior, a suite of behaviors that work for the body it has right now, the broken body. And that's a feasible way of doing it, in my opinion. Like, you don't need these robots to be 100% functional all the time. And, that's a near-term solution. And I think it's kind of encapsulated in the need for adaptive control that these soft robots have anyway. So that's a straightforward method of kind of implementing that.
I'm curious, through the project you work on, is this something was maybe struggled to understand, or was kind of counterintuitive or exciting? I don't know, sort of the process, what you're working on. Any moments like this is counterintuitive or exciting, or I didn't saw that should work in that way? Any moments like that?
Oh yeah, so man, I think there's been a couple, but the most recent one is when we, again, looking at these granular grippers, what we want to do is provide ways for people to have their universal grippers work better, not necessarily needing to go into vast design spaces and control spaces, but sometimes the simplest solutions are the best. And one of them that we had was basically adding an amplifier, like a vibration amplifier, onto the top of the balloon, and then we could vibrate the grains. So we looked through the literature and we saw, vibration was used to unjam the grains, basically to reset them to a fluid-like state so they can push onto a different object and then solidify and pull off again. But it hasn't really been used for control that much. So we had this this paper that is on arXiv right now, where we changed the sort of the signal properties of the signal, the vibration, the amplitude, and we show there's a strong dependency on the ability of that gripper to grip our test objects. So what it means is basically we've been looking for a way to do this co-optimization problem with a jamming gripper. And the jamming gripper, normally what you do is you just have a vacuum pump and you turn it on and off. So you have like a binary control, which does speak to the kind of material computation aspect of things, right? Where your control is 1 or 0 and it's super simple and it's great. And with our printed membranes, we can get program deformations in them. So we can make them twist, for example, to pick up coins and things that these jamming grippers normally can't do very easily. But it opens up this entire range of behaviors of control that we can now co-optimize with the morphology. So, I mean, the results from that were pretty stark in terms of it's always better regardless of the frequency, but it's very specifically certain frequencies that it works well at. And that was a project that was a master's student's thesis. A guy called Raghav, and he came to work for 6 months, and we did the whole thing. And at the end, it was like, wow, that's pretty interesting. So yeah, I think that's probably the most recent sort of wow moment that we've had.
Excellent. So I'm curious to ask you, do you think maybe other questions, maybe in soft robotics field, also maybe on robotics, do you think still not really asked by the community? You think when you look, why we don't touch this topic? Because part of it, maybe we avoid a little bit risk to go for this area because no one touched it before. I'm curious about your point of view. What kind of questions do you think maybe through your work, you still, this question are not answered yet. When no one initiates this question, why? I don't know if you have any thought about that point.
I do, but I kind of think that the answers are kind of in the questions. Like, why don't we do more with untethered soft robots that could actually go out and sense things? And the answer is that I don't think the field's quite ready for that. Like, we have so many problems, so many interesting research directions to go in, and that that there are untethered soft robots out there. And that work is all really impressive. But if you think about an autonomous agent, so for example, the types of robots that we do in our group as rigid robots, they're basically like tracked vehicles, and they've got sort of SLAM packages on top of them, so they can sense the environment, and then they can build a map. And then they can sort of move around on that map autonomously. Like, we can't do that with a soft robot right now. And I think the field isn't really directed towards that yet. I think the field, things like state estimation are still difficult. If our robot can bend in an infinite number of ways, how is it bent right now? Is a really tricky question still. So I think a lot of the sensing advancements that we've had are really around sensing the robot itself, kind of internal sensing of the robot's own state, which makes sense, right? Because that's what we need as a minimum to be able to get any decent control out of it, any behaviors. But there isn't too much environmental sensing. Now, there obviously is some in terms of pressure sensing of an actuator touching an environment, but the wider context of what's going on, the type of broader knowledge that you need for actual autonomy, where you can just let a robot go on a mission. I don't think soft robots has really tackled that yet. And coming, in the field robotics group, that's something that we're going to have to tackle sooner rather than later. But it's not, I don't think it's really currently covered by soft robotics research, although I am happy to be corrected on that. And I think maybe one more that I've mentioned before, sort of in the multi-level evolution paper, was like, we make our robots out of these awesome, wonderful, compliant, stretchy materials, but wouldn't it be awesome if we could just hook up our design algorithm to another design algorithm that is designing bespoke materials for us? Like, so when we use when we sort of do a standard soft robotics thing, like, so we're casting something, right? We're using PinkSil or EcoFlex, and these things come from, I mean, they're good, right? But they're used because it's relative, and in relative terms, it's relatively easy to work with them. They're available. They have some mechanical properties which link up to the mechanical properties we want to see. But they're for prosthetics. They're like for prop masks and stuff. They're not designed for robotics, is my point. And I think we could get a long way by evolving or learning or investigating spaces of materials that are specifically robotic materials. Things where we start to have these materials that integrate the sensing into them already, so the material can sense itself. And then we can just create structures out of this material, and that structure can sense itself too. And as we, talked about coupling a lot. So if we couple the search process of bespoke robotic materials with a search process of bespoke soft robots, then you could hit this kind of evolutionary arms race thing where they're both optimizing each other. It's like a co-evolutionary free lunch, and that's the sort of thing that that's very exciting. But again, like we're not there yet. We don't have it yet, and that's okay.
Yeah, I really like this point. This is a really excellent point, because when you mentioned about the robotic EcoFlex Dragon scan, it's easy to use maybe, and I had experience. I was working on any conductive polymer a couple of years ago, and this material, it's still, I think, because it had this trade-off between the mechanical performance, very low mechanical performance, very slow, but it's operated at low power, and it can be work as sensor actuator at the same time. But seems it's hard to understand. And that leads me to the question for you. Do you think when we speak about real world application, that's something realistically, we need something to work with so that you can understand and test our ideas? On the other side, we have the material part, morphology, control, environment, this kind of combination here. Do you think for you, the material part, maybe what kind of material can operate at cyclic load and also has low hysteresis? So it's kind of characteristic for you. Do you think maybe there's something room here missing between the material part, morphology, control, and how we combine all that? How do you see this combination for the material selection here?
Well, I think, I think if I knew the answer to that fully, I'd probably be working on that right now. But I think, there's definitely scope to improve our base materials. We've chosen these materials because they're decent. They provide basic mechanical functionality so that we can make them into a variety of shapes relatively easily. Again, I hate casting things, but relatively easily. I think a really interesting breakthrough would be if we could get our printable materials up to the same standard as even those basic materials. That would be a good first step. Because the printed materials that we have on our polyjets are really, really good in terms of we can spit out lots of designs very quickly and physically characterize a design space to some extent. But the elongation at break, for example, the basic mechanical properties of these printed materials are still not where we need them to be. And if we can get the printed materials up, then it means that we can just explore these design spaces a lot more freely, and we can make things that are more useful. A lot of the kind of printed things that we create at the moment, we subsequently recreate them. Once we found a good morphology through printing, we then recreate it in casting. But if we do that, we can't do multi-material very easily, for example. And the polyjet lets us do very simple multi-material builds that are really nice. Variable wall thicknesses and all of this stuff, which I think is a key to unlocking this sort of material computing that we need. I think the answer is in additive or subtractive manufacture rather than in casting and molding. But to bring them together, interesting. I think So one thing to think about is kind of the philosophy of soft robotics, which to me is the philosophy of embodied cognition. Embodied cognition has all of these components that we've mentioned, but the actual concrete implementation of embodied cognition algorithms, again, is quite scant in the literature. And if I was looking for a way to tie all of these things together, the first thing that I would do was develop a mature framework that allows us to consider, maturations in these different elements, but also what happens at the interfaces between them. Because that's the really interesting science is what happens when you get material plus morphology, material and morphology plus control in the environment, and all of these different, they are in a way silos, but when you break that down, that's the cool stuff. And that's, I think, having a framework in which where people have some kind of degree of agreement on what, because if I say I do embodied intelligence and 10 other people say they do it, they probably have 10 different definitions in their head of what that is. So having like I say, just a framework where we can say, look, refer to figure 1, and this is what I mean when I say I'm talking about embodied cognition. And then if we do that, that allows us to transfer those ideas meaningfully into the field. And it might, ideally it would lead to future research directions that would answer the really, really difficult question that you asked me.
That's excellent. So since we close the end, I have a few questions. Maybe the first thing related to morphology, and especially about multi-material design, not printing, but designing multi-material. When we look, since you're already inspired by evolution and part of your study, when you look to animals have this certain structure for multi-material, and the question is how evolution can come up with this design. For example, I like this example, this fish is called Arpime in Amazon, and they have this multi-layer for soft and stiff material. That's when the predator like piranha fish cannot really eat them. And a question to you, do you think in soft robotic, when we try to use different materials, significant different materials to design certain functionality, do you think we understand how we can combine different materials to achieve certain goal in a certain intricate design, or maybe simpler design? I don't know, but I'm curious, how do you see the combination of different mechanical materials in one structure?
Yeah. Again, it's a difficult one because it comes back to the environment, right? So there's been a lot of work on the kind of evolution of multi-material structures. There's these algorithms, ESO and BSO, and they're basically evolutionary topology optimizers. And there's some of them you can do multi-material, but then it's what happens when you inject a behavior over the top of it. So, like, there are ways to do it, but it's kind of reductionist in a way. Like, you need to say, like, if I'm a fish and I need my jaws to snap with this force, then all of a sudden that's a problem you can kind of solve, right? But when you're talking about, I need my jaws to snap with this force and I also need to be able to do all of this other stuff as well, it's tricky, and it depends on the application of the robot, right? Which bits matter and which bits don't. I think there's a lot to be said just in terms of marrying a material layout inside a structure. It's very hard to actually even have a kind of overarching structural optimization and then filling in the different materials as well. And there's, you potentially do that with metamaterials. If you've got like a voxel-based process, then you can have voxels that are 10 by 10 by 10, and you can put different voxels of material inside that voxel, and suddenly you can build up these structures that do that. And the design of that needs to be either automatic, so kind of based on here's a shape I've created, here's a behavior that I want, find me the material composition that lets me do it, and it will kind of paint over with the materials that allow it to do that. Or you could potentially, I guess, yeah. So that's probably the main way to do it. You couldn't really do it as a direct representation because you hit all of these dimensionality problems. But an indirect representation you could do, as long as it's not brittle. And ideally, if you can stick gradients into the problem, then it becomes a lot easier to do as well. Mm-hmm. Or if you can put the entire problem into some kind of differentiable physics engine, then all of a sudden you've taken one of those bits that you're not naively, but really it's difficult to search through, and you've turned it into a gradient-based optimization problem. And then that's how another way that we could kind of solve the problem of doing materials and morphology, and then coupling that with control, make as much of that differentiable as possible. And then the benefit is, it's differentiable physics, so you can put it in a physics simulator and tune the physics simulator to reality. Tie everything together.
Yeah. So two questions left. The first one, I'm curious about your future, maybe vision about your work. Where do you see that goal of your work? Maybe that's what I want to do, maybe, yeah, later on. a future vision for your work.
Yeah, I think there's a couple of things. So I've kind of got a researcher's hat on, but also the Cyro hat on, which is like, let's go and apply it and get 5% GDP or whatever we can get. In terms of coming from my academic background, what I really want to do is recreate these kind of high throughput processes in a soft robotics context. So it's either we do high throughput materials specifically for a soft robot, or we actually do high throughput soft robotics. And then that's a really good way to explore a design space and make it physically meaningful when you do it. And you can tie this all into kind of the multi-level evolution architecture as well. So instantiating that fully physically as a system. Ideally what we do is we be bringing in collaborators and having this distributed system where the different research institutions have different strengths and weaknesses, but together they could combine them to make one of these really difficult to instantiate systems, and then everyone sort of shares in the benefits of that. So that is definitely a bucket list item. And I think in the kind of medium to longish term as well, what I want to do is I want to see the soft rippers that we're producing turned into products that are used by people. So we want to actually have out of the lab and into the field. Like I said, we're a field robotics group, and we need things to work, and that's really one of the big challenges for us. Is how do you, even in back to material properties, like how do you get something to do 10,000, 20,000, 50,000 cycles, kind of thing. And the materials and the material science is obviously a well-established field in its own right. But I think maybe looking at bespoke robotic materials is a way to meet those demanding needs of these really difficult sort of environments, orchards or vineyards and things like that. So yeah, that would be great to see as well.
I don't know if you have any final words like to say for robotics community and soft robotics listening to you. Any final words you'd like to say?
Sure. Well, like I said, we're relatively new on the scene. We've had one article in Sovo, we've had a paper in RoboSoft, and we've got another few kind of that we're working on. We're really eager to start working with other people in the community as well. So please have a look at our papers. If we are doing stuff that you think is interesting, just reach out, and we'll be happy to talk to you.
Wonderful. Thanks so much, David. It was so inspiring, and such an honor to have you again at the podcast. Thanks a lot for your time. Thank you.
Thank you.